Thank you to the organizers for the slot in the schedule. So I'm going to talk in the next 50 minutes about exceptional flux compactification. So flux compactification is based in this work in collaboration with Giuseppe Di Viteto and with Diederik Rust. So during the last 10 years, people have been working on flux compactification, so we keep on working on them. But we will restrict to a subset of them, which we decide to put the word exceptional. So the first question is why they are exceptional. And then there are two main reasons because we consider that they are exceptional. The first one is because they preserve an exceptional amount of supersymmetry, and indeed they preserve the maximal amount of supersymmetry in 4 dimensions, so maximal supersymmetry. And then they give rise to maximal gauged supergravities in 4 dimensions. The ingredients then of these theories are just the supergravity multiplet, which contains many fields inside bosonic and fermionics. And then these theories can be deformed by some deformation parameters, and they give rise to something that in the supergravity context they are called gauges. Because of the amount of supersymmetry they preserve, if you want to embed these supergravities in string theory, you need to go to type 2 strings, either type 2A or type 2B. And then also because this amount of supersymmetry you cannot include, or let's say these supergravities are consistent with not having with string embeddings without branes. Because if you have branes, you break some supersymmetries. So then, this was the first reason. The second reason is that these supergravities come out with an exceptional global symmetry in 4 dimensions. And in particular is the E7 exceptionally group. So, the consequence of having this global symmetry is that all the fields and deformation parameters in the supergravity arrange into different representations of the global symmetry group, of E7 in this case. So the bosonic fields are the metric, the vector fields, and the scalars. And these numbers are off-shell, let's say. These are not all physical degrees of freedom, but the metric is a singlet of E7, the vector are 56, which is the fundamental representation of E7, 28 are electric and 28 are magnetic, and the scalars are the physical 1 and 70, but if you count them all, because they expand the concept, but you can fit them all in the 133 representation of E7, which is the adjoint. With the fermionic fields, something similar happened. There is some subtlety with the gravitini, because you have 8 gravitini, and there is no representation of E7 of dimension 8. But you can fit the gravitini into the 8 of SU8, and SU8 is the maximal compass group of E7, is the R-symmetric group of maximal supergravity. And you also have 56 dilatini. An interesting feature is that the deformation parameters of this theory, which in the supergravity language you call it the event tensor, which is the way of deforming the free theory, these deformation parameters also fit an irreg, and in particular they fit the 912 of E7. This means that there are 912 deformation parameters in maximum supergravity. And the correspondence to string theory of this deformation parameter are the fluxes. So the first question you can do is, okay, can I get 912 deformation parameter fluxes from type 2 strings? So then, well, let me tell you that the fluxes are nothing but the field strength of the 10-dimensional gauge fields when you restrict only to be threading the internal space. So the first thing you can do is just to make a quick finger counting about, okay, which fluxes can I have? And then you go to your fields and then you say, okay, you have the metric or the field line. So then I can compute the field strength of the field line. And if you count according to symmetry and anti-symmetry indices, you get 90 guys here. You can do the same with the B field, with the dilaton, and with the Ramon P forms. These are the spectrum you know in the type 2B string. If you compute the field strengths and then you make the counting, you get 148 fluxes, no more. But then you have to get, according to duality, to global symmetry arguments, you have to get 912. So clearly this number is smaller than this. So what is happening? And that's why people originally introduced a bunch of new objects you call non-geometric fluxes, but are things you need to put in order to fit the representations. These objects are really nice, or let's say, they are really interesting for 2 reasons. Theoretical reasons, let's say, and phenomenological reasons. The first thing, concerning theoretical reasons, there's one question is whether these fluxes can give rise to genuine stringy background, because at some point these fluxes are related to the global symmetry. The global symmetry of the theory is related to the duality of in a string realization. And duality accounts for stringy features like a wrapping or a strong weak correspondency. So it's really, probably there could be the origin of the flux is really stringy backgrounds. Another big question is, okay, if I have one of these non-geometric backgrounds, can I lift it to 10 dimensions? And then we had some talks in this conference about this. Another big question for me is which is the object underlying those sources, because when you have, for instance, p-branes radiate Ramon-Ramon p forms and Ramon-Ramon forms. So which are the sources of these non-geometric things? And then also whether, in order to describe properly and understand these backgrounds, one has to go beyond geometry, and then for this, so there are some approaches based on double field theory or double geometry or generalized geometry. There are some approaches in the literature. So just to make you an analogy of what is the problem somehow in a more naive way or in a, in a cartoon way, it's like when you go to a rock festival thing and then you have the source, which is the band that is playing. Because of the source you have a background of 10,000 people around, and if you are a test person and you want to move from one point to other point, either for a beer or to meet a friend, you will discover that if you just flow through the geodesics, you deviate for the straight line. So it's really the fact that the background modifies also geometry. And the question could be like, just by studying the background, can you infer who is playing, which is the source behind that thing? So this is for me the big question about these non-geometric fluxes, in the theoretical level. Then in the phenomenological level, they have been shown to contribute or to help you to find the Sitter solutions. And for instance, this is a histogram about the different contributions to the energy in a de Sitter solution in the literature. Then you can see that there are some contributions coming from the Neversar sector, from the metric fluxes, for all the Ramon-Ramon fields. This example was in Sun N=1 theory, so there are also grains. But there were contributions coming from the non-geometric fluxes, so they help in the problem of moduli stabilization. So what we would like to do is to say, okay, so let's explore moduli stabilization in maximal supergravity, considering, in general, fluxes of every type. Which is the good thing of going through a supergravity approach. The good thing of a supergravity approach is that it's rigid, it's solid, and it's well built, irrespective of whether you have a string embedding or not, or that is another problem. And the good thing about the the moduli stabilization thing, or the problem of study scalar dynamics, is that in maximal supergravity, everything is encoded into these two objects, which are called the fermionic mass terms. Why these are called like this is because if you go to the fermionic mass Lagrangian, you see that there is a coupling between the gravitini, and it's determined by this matrix, and there is also a coupling between the gravitini and the di Latini, and there is also a coupling between the Latini and the Latini, but this is how you can build this coupling out of this one, so it's not independent. So I will concentrate all the time in these two guys, this mass matrix and this coupling term. If you know these guys, you can build these quantities, which are the sources of the scalar potential. So, knowing these guys, you know the scalar potential. Moreover, if you know these guys, you can also build this tensor with Fourier indices, and by demanding its self-dual part to be zero, this is the equations of motion for the scalars in a maximally symmetric solution. So this corresponds to the critical point condition. And even more, by computing the eigenvalues of this mass matrix here, you can check how many of them coincide with this number, with 1/6 of the energy. And then you compute the amount of supersymmetries you have perceived. So, knowing these two matrices, knowing these two quantities is basically winning the game. You can compute everything if you know them. So, what we did in the paper? What we did in the paper was nothing more, nothing less than connect from fluxes, given a flux background. I will tell you which are the fermionic mass terms they induce, and then I can compute solutions or whatever. Or the other way around, if you give me some fermionic mass terms, I can go back and I can tell you which is the flux you need in order to have a string embedding of this thing. The procedure is really horrible as everything related to maximal supergravity, but just to sketch how it goes a bit, it's like you start with your fluxes, an H flux, a metric, a non-geometric Q, a Ramon-Ramon, all the fluxes you can imagine. Then you can go to one layer of unification, and then you build these four objects, which are four tensors transforming under this symmetry loop. Then you can unify all these four guys in a unique guy that belongs to E7, because this group is a subgroup of E7. And once you are here, this is the guy called the embedding tensor of maximal supergravity. And up to here, everything is field independent, because these are constant fluxes. I go different layers of unification, but everything is field independent. And arrived at this point, you can contract these indices with some matrix which depends on the scalars. And then you go from what is called the embedding tensor to what is called the T tensor. But it's nothing else than dressing up the embedding tensor with the scalar dependence. Once you have this guy are still E7 indices, and because SU8 is a subgroup of E7, you can decompose under SU8. And under you have the different components of these guys decomposed under SU8, you can take some traces, and then you end up with the fermionic mass terms. So, Okay. So what are we going to do? We are going to do two things, basically. We can use this correspondence, basically, to having some flux backgrounds, build the fermionic mass terms, and compute maximal symmetry solutions, or the other way around. Given some fermionic mass terms, I can build, or I can work out which are the fluxes generating them, and I can say something about the non-geometric origin. An example of the first is an example based on some type 2A orientifold models that people worked out some years ago, and then we restrict our life to considering only Ramon fluxes, never-sharp flux, and a metric flux. So let's say, guys having a well-defined origin in dynamics. By using all this correspondence, we work out the fermionic mass terms, we compute the set of all the solutions to this flux background. Then we found that there are 4 anti-de Sitter solutions, 4 critical points, which are ADS. We correspond that there is a unique deformation, or in the language, the supergravity language, there is one gauging underlying all these critical points, which is this gauging, which contains a semi-simple part and an nilpotent part. And we also found that all the solutions correspond to compactifications on SU2 times SU2 manifolds. These are the 4 critical points. The first one is supersymmetric, n equal 1 supersymmetric, like spontaneously, so it breaks spontaneously supersymmetries. The other are non-supersymmetric. We found that these 2 are stable, the supersymmetric of course, but this was non-supersymmetric, so it's far from being trivial, the fact that it's stable. Then these 2 solutions were unstable. This is based on the mass of the lightest mode and compared with the Breitelon and Freeman mode, and these were the different values of the energies of these 4 critical points. So we were happy because we found this stable and non-supersymmetric critical point of maximal supergravity, which have an embedding in string theory with purely geometric fluxes. But then we also went the other way around, and then we took some gaugings in the literature of supergravity that are called CSO gauging, which are basically SO-PQ gaugings, and then you can contract some of them to some of them these pluses and these minus. And then what we did is, okay, let's use our correspondence, and using our correspondence, we were able to define the matrices, which are these 4 matrices. Determining this gauging, we were able to build them as a function of the fluxes, and only this guy is the Ramon 3/4 flux, and only this guy is the never-sharp 3/4 flux. The other guys are non-geometric fluxes. So what we did is, okay, well, this is the table with all the different flux matrices you see here. These are the deformations in maximal supergravity. This is the value of the energy. These are the value of the different masses of the different scalars, and what we showed was that these gaugings correspond to non-geometric fluxes in the string theory side. So just let me summarize. First of all, global symmetries, dualities in supergravity, demand unconventional non-geometric fluxes, and these non-geometric fluxes come out with a lot of interesting questions, both in the theoretical side and also in the phenomenological side. What we did in this paper is try to exploit a bit the connection between string flux compactifications and gauge supergravities, just to try to shed a bit of light upon these questions. And in particular, there are more things you can do here, and especially related to the talk yesterday about Bianchi identities, because in the supergravity side, the consistency of the gauging is given by a set of quadratic constraints, and that is fixed. And those things, when you go to the string theory side, they translate into tactile cancellation conditions or Bianchi identities, etc. So in the supergravity side, everything is kind of done. The problem is embed everything in string theory and try to see which is the algebra structure underlying these things, like from Lie bracket to Cohen bracket to Reutenberg bracket, what else you need. And then, as a quick summary of the results in the phenomenological side, what we happen to find is that we found that very simple gaugings, like nilpotent gaugings, happen not to give moduli stabilization, but they are good when it comes to go to string theory, because they correspond to only gauge fluxes. And this is done in this paper. Then, completely semi-simple gaugings, like the SO8 gauging, are good for moduli stabilization. Even you can get the Sitter, you can get many critical points, but when you go to the string embedding, they happen to correspond to non-geometric fluxes, so here the problem is there. And then, in some intermediate examples, we work out, and there are more examples in the paper by Guido. There are some intermediate gaugings, we call it, which contain a part which is a semi-simple part and a nilpotent part. And these gaugings are good because some of them, well, they produce moduli stabilization, so good in that sense. And when you go to the string theory realization, they also come from geometric fluxes. So there is an intermediate step in which everything happens to be nice. So, thank you.
So you never the brains on the string theory side? You put this.
The point of these compactifications is that they preserve maximal supersymmetry.
Right.
So there cannot be breaks. And when you compute the quadratic constraints in the supergravity side, then you translate into the string theory side by using these flux supergravity themes. What you get is that all the Tadpole cancellation conditions you get in string theory are equal to 0. So these are somehow flux backgrounds which are consistent with not having breaks in the string theory side.
But would you expect to embed all of these supergravity solutions in the string theory? Because we kind of, concerning non-geometric fluxes, we kind of know that, say, the Q flux and the R flux are not independent of each other. But you treat them as independent, right?
Yeah. Well, that's the big question indeed. But I could say that if you want to embed all the supergravities in string theory, then you need to know which is the higher dimensional origin of all the non-geometric fluxes, or which is the higher dimensional origin of which are the gauge fields you are missing, whose field strength are those non-geometric fluxes. So maybe you need to go to an off-shell formulation of supergravity, or I don't know what, but that's the question. That's the big question.
First, a word of caution on geometric versus non-geometric, in the sense that, for instance, SO8, of course, is geometric in the sense that we can obtain it by compactifying this in a sphere and theory, for instance. In your language, it would be non-geometric, of course, because you're somehow considering always deformation, you call geometric deformations on the torus.
Yes.
You think about twisted tori, things like that. But beside that, you said, of course, that those fluxes that you studied are non-geometric, at least in this language. Did you try to consider also some duality orbit or something? I mean, I know that you work on this, so I don't know if you try to.
Yeah. Well,
to see whether there is any point of this orbit with
having a
geometric description.
Yeah. Well, first, with respect to your comments, you're perfectly right, but it's true that you can get the SOF gauging from dimensional reduction of M theory on the surface here. But then it's true that then you have to go through cosset spaces, and then you cannot be systematic. You have to go space by space. So we did this because we wanted to be systematic. So that is perfectly true. And then, regarding the question of whether non-geometric backgrounds, they will have somehow a geometric representative, we tried to do for this type 2b, we moved to type 2a by 3 dualities, and they were still non-geometric. So, but we didn't do a detailed orbit study just to see whether these guys lie in an orbit passing through a geometric representative. We didn't do. But yeah, that's.
You have a paper on something like that?
But only at the 7th dimension.
Okay.